This is an example problem in using the Biot-Savart Law. So for my Stark State students, you'll find this in the Chapter 30 notes on slide 4, and it's about finding the magnetic field at the center of a loop of wire. So the Biot-Savart Law tells us that whenever we have a current carrying wire, we always create a magnetic field that's perpendicular to the current. It's perpendicular to a radial distance that is on a line moving away from that current, and the strength can be calculated as mu naught, the permeability of free space, times the current divided by the constant 4 pi times the cross product of our path vector ds crossed with the radial direction vector r hat divided by our radial distance r squared. So for the case of a wire that's bent into a semicircular loop, we can break this into 3 parts. The first part is a current carrying wire traveling in towards the exact center of the loop of wire. The middle part would be traveling along a constant distance away from the center, and then that current exits heading away from that central distance. So just to lay out our coordinates, I'm going to call I hat the x direction, horizontal, j hat the vertical direction, and k hat is going to be coming out of the board. And remember those directions: right hand rule, fingers point in the x direction, close your hand towards the j direction, your thumb shows you which way the k direction is. So if we're on the radius here, our path element ds is in the exact same direction as our radius. So if you have a cross product of parallel vectors, the cross product of parallel vectors is always 0. Now on the final segment C, they aren't parallel, they're anti-parallel, going in opposite directions. So that means we're still going to get a 0 cross product, because the sine of 0 and the sine of 180 degrees are both 0. So the final part, things simplify a lot, because we're traveling at a constant distance, the radius of our circle, which I've called A. So that means if we think of our path element ds is going to have a size equal to our radius A times our change in angle that we move along that path d theta. Now, to calculate our Biot-Savart integral, we need to take a look at the cross product of ds, which is moving along the wire, so our fingers would be pointed in the direction ds. Our palm needs to point in our direction r hat, so our palm points to the middle, we close our hand, and our thumb is pointed into the board. So x marks the spot. We have a magnetic field that's going to be in the minus k hat direction. So that means that when we go to sum up our magnetic field using the Biot-Savart law, our magnetic field is going to be our constant mu naught times I times our element of path ds divided by 4 pi, and our radius would have a constant size of a squared, and as I said, it's in the negative k hat direction. But since ds is ad theta, we cancel one of those a's that is in the numerator and in the denominator, so we end up with an integral, or an integrand rather, of dB equals negative mu naught I over 4 pi d theta over a in the k hat direction. Well, all of these are constants except for d theta. So the integral of d theta is just theta. So for any loop of wire, the total magnetic field is based on the total angle that you travel around that central point. And it also means if you start looping this wire around multiple times, it's like you've gone through 2 pi, 4 pi, 6 pi, however many pi radians, you get a stronger magnetic field. Well, in terms of thinking about it as turns, rather than thinking about it as an angle in radians, for n loops, we just have to multiply by the number of n, where n is our total number of loops and 2 pi radians for each complete circle. Thank you.